Hey there everybody, welcome back to another lecture video. This time we are going over chapter 8, and this time my lecture PowerPoints are actually named properly. In this chapter we're going to be looking at stoichiometry, and the stoichiometry is essentially how we quantify quantities in chemical reactions. Now, let's start off just by talking about one of the important reactions that we may want to quantify. Let's talk about global warming. So global warming essentially means that there is too much carbon dioxide gas. Now, the combustion of fossil fuels, such as octane, which is shown here, produces water and carbon dioxide as products. We saw that in the last chapter. And carbon dioxide is a greenhouse gas that's believed to be responsible for global warming. Now, so greenhouse gases, they act like a greenhouse, like the glass in a greenhouse. And they allow visible light energy to enter, but prevent heat energy from escaping. And so that's what a glass house does. A greenhouse, sorry. It lets light energy in, but because it's enclosed, the heat and the warmth stay inside. So outgoing heat is trapped, as you can see, by the gases, and carbon dioxide is one of those gases that does this. So the more carbon dioxide in the air, you can imagine, the more heat will be retained every day that the sun shines on us. Now, let's consider, oops, let's consider the reaction for this, and we're going to do an analogy and look at some recipes for pancakes. But before we get there, let's just look at the reaction for carbon dioxide formation here. So for the combustion of octane, it's actually C8H18, and it takes two molecules to react with 25 molecules of oxygen gas. If both of these are in abundance, then we get the reaction. We get 16 molecules of carbon dioxide. Now I'm saying molecules, but if we were to scale this up, this would be moles. 2 moles of liquid octane and 25 moles of oxygen gas will make 16 moles of carbon dioxide and 18 moles of water. Now what this balanced chemical equation shows us is that 16 moles of CO2 are produced for every 2 moles of octane that are burned. And since we know the annual consumption, or since we know the world's annual fossil fuel consumption, we can estimate the world's annual CO2 production. And we'll do that calculation a little bit later. We'll start with the amount of gasoline, essentially, that we sell each year, and we'll look at how much carbon dioxide that would lead to if it all burned, and then we'll compare that with numbers of increasing CO2 concentrations that we measure every year. So we can do that, and we will do that. Now, what stoichiometry is essentially is the relationship between ingredients. Stoichiometry, the relationship between ingredients. Now, it's the numerical relationship between the chemical quantities in a balanced chemical equation. This allows us to predict the amount of products that would form from the amount of reactants that we actually have. And we can predict how much reactants we would need to get a given amount of product. And so when we are able to use stoichiometry efficiently, we can then predict how much of one reactant is required to completely react with another reactant. And so to get you guys in the mindset of this, let's take a look at making pancakes and some relationships between ingredients. So here we have a recipe for the numerical relationship between the ingredients and the number of pancakes. So here you can see 1 cup of flour, 2 eggs, half a tablespoon of baking powder. We'll make you some rudimentary pancakes here. Now I always add butter and some salt, maybe a little vanilla flavoring, but that's just me. A little bit of sugar too. There's no sugar in any of these pancakes. So this is a simple recipe for some pancakes. Now, what this recipe shows us is that, for example, if we have 2 eggs, we definitely have enough eggs to make these 5 pancakes. And we can write this relationship as 2 eggs to 5 pancakes, right? And so then if I had, let's say, 8 eggs, and I wanted to know how many pancakes I could make from 8 eggs, I could use my relationship. I could remember that every 2 eggs would give me 5 pancakes. My egg unit would go away. My pancake unit would be all that remains. 8 divided by 2 times 5 is 20. So I'd actually be able to make 20 pancakes if I had 8 eggs. And you can see that we could do this. Let's see. So, sorry, actually had images for all of the worked out math we just did. So you can see that we could predict how many products we would get, in this case pancakes, from a starting number of eggs. So in a balanced chemical equation, it's the same way. The balanced chemical equation is the recipe for how these reactants will combine together. This following equation shows you how hydrogen and nitrogen combine to form ammonia. So you can see here it takes 3 molecules of hydrogen, 1 molecule of ammonia. Letting these things react together provides us with this equation and the products. The 2 ammonia come from the 3 hydrogen and the 2 nitrogen. So a balanced chemical equation here shows us that 3 hydrogen molecules react with 1 ammonia molecule. So we could make relationships here. We could say for every 3 hydrogen molecules, we get 1 ammonia, or we need 1 ammonia molecule. I'm sorry, 1 nitrogen molecule. And that in either case, 3 hydrogen molecules would produce 2 ammonia molecules, or 1 nitrogen molecule would produce 2 ammonia molecules. Right? We're making all of these relationships from the balanced chemical equation. 3 to 1, right? 3 to 2, 1 to 2. That's where these are coming from. Now, since we don't normally deal with individual molecules, and we often deal with moles, let's just say these are moles. Same exact ratios, but now they're moles. Okay, so let's do a practice problem. Let's say if I have 3 moles of nitrogen gas, so I have 3 moles of N2, and more than enough hydrogen gas. So whenever we say that, we usually just refer to this as being in excess. So I've got 3 moles of nitrogen gas, I've got excess hydrogen. How much ammonia can I make? And so to solve this, we would just need to know the relationship between the ammonia, which is our limiting factor here, because if we have excess this stuff, that means we have more than enough, then presumably this is what's going to run out. This is the limiting. So we would just need to look at the relationship between the limiting and our product. Okay, so 3 moles of nitrogen gas, we remember that every 1 mole of nitrogen gas, according to our formula, makes 2 moles of ammonia. Moles of nitrogen gas goes away. 3 times 2 is 6. So the stoichiometry here has shown us that we can predict how many moles of ammonia we could foreseeably end up with from the starting reactant, in this case, the nitrogen. We could have done the exact same thing with the hydrogen, started with some number of hydrogen gas, said the ammonia was in excess, the nitrogen was in excess, and then again, seen how much ammonia we could actually make. Okay, so another example of this, like I said, would be to say, oh, hey, I've got 15 moles of H2, right? How much ammonia can I make? And you'd have to fill in the 3 moles H2 to every 2 moles NH3. Now this only works when one of the other reactants is in excess. So nitrogen's in excess. We don't have to worry about it. Sometimes that's not the case, and sometimes we do have to come back and worry about that. Okay, so let's talk a little bit more about when you don't have enough oxygen when you're burning octane. So the balanced equation for the combustion of octane, C8H18, 25 O2s, 16 CO2s, 18 H2Os. This shows 2 moles of oxygen require 2 moles of octane. Require 25 moles of oxygen. So in the case of the octane, a shortage in the O2 will actually cause side reactions to happen. If there isn't enough oxygen, then we actually end up with some carbon monoxide and ozone as products as well. We're not going to worry about that in terms of like calculating out how much of the side products would form. But just wanted to point that out since we are talking about gasoline as the example here. In the 90s, there were amendments to the Clean Air Act that required oil companies to put additives in the gasoline that actually increased its oxygen content so that there would be more oxygen available for these reactions. Now, the chemical equation contains conversion factors between moles of reactants and moles of products. But we're often interested in the relationship between the masses of reactants and the masses of products. So the general outline for this type of calculation is right here shown. So you see mass of A can be converted into moles of A. And for that, we need to know the molar mass of A, which if it's an element, we get it off the periodic table. If it's a formula or a compound, we have to add that up from the periodic table. Then we can use stoichiometry from our balanced chemical equation to relate moles of A, let's say A is octane, to how much oxygen we would need, let's say moles of B. And then once we've figured out that number, moles of B, we could then convert that back into grams. And that's usually the pathway that we are going to take. So for example, let's say, what mass of carbon dioxide is actually emitted by an automobile for every 5.0 10 to the 2 grams of pure octane used? Okay, so for that, we're basically saying that we have 500 grams of octane. Now for that, we're going to need to figure out how many moles of octane that is, right? Because this is where we are. We're at mass of A. We want, so octane is A, carbon dioxide is B. We want mass of B, but to get mass of B, we need to know moles of B. To get moles of B, we need to know how many moles of A there was. To know how many moles of A there is, we have to convert our mass of A. So that's the steps that we're going to be taking. Now, I've assumed that you guys are capable of actually calculating these, but I threw them in here so that we wouldn't have to do it during this video. Now, if you are struggling, remember this 114.13 number came from taking 8 carbons at 12.011 grams per mole and adding them to 18 hydrogens at 1.0079 grams per mole. So that gets you to about 114. So that's where that comes from. This is how we'll convert, right? We'll go from mass of octane into moles of octane. And then our balanced chemical equation said that every 2 moles of octane produced 16 moles of CO2, and then again moles of CO2. 1 mole is 44 grams per mole. And this is 2 oxygens at 15,999 grams per mole, and a carbon at 12. So that's where 44 comes from. If you do that and you plug in all your numbers, you should check to make sure that your math comes out to be the same as my math, but 1.510 to the 3 or 1,500 grams of carbon dioxide ends up being put into the atmosphere. And that's just for 500 grams of gasoline, which is nowhere near the amount of gasoline that would be inside your gas tank of one car, right? Let alone the annual consumption of gasoline. All right, but that's just an example of how we would do this, where in this case, the oxygen was in an extra supply. All we had to do was look at how much octane we had to see how much CO2 we'd get. But let's make it a little more realistic. So coming back to our pancake example, remember the equation? 1 cup of flour, 2 eggs, half a teaspoon, of baking powder, and 5 pancakes. So suppose that we actually have 3 cups of flour, 10 eggs, and 4 teaspoons of powder. Well, then how much pancake can we actually make? And so that's where we're going to get to these concepts here. Limiting reactant, theoretical yield, actual yield, and percent yield. So let's work through this. Okay, so how would we do this? Well, the first thing we would do is we would figure out how many pancakes we could make from each of the individual ingredients. So for example, the 3 cups of flour, we remember from the equation that 1 cup will make 5 pancakes. So that would be 15 pancakes. The 10 eggs, right? Every 2 eggs makes 5. So 10 eggs is going to make a lot. 2 eggs is 5. This would be 25 pancakes after we, right? 10 divided by 2 is 5. 5 times 5 is 25. As far as the 4 teaspoons go, I'm going to keep saying tablespoons. Every half a teaspoon produces 5 pancakes. This by far makes the most number of pancakes, 40 pancakes, 8 times 5. All right, so what we see here is the theoretical yields of each of these ingredients is actually different. So how many pancakes can we actually make then? If we did this, if we actually used all of our ingredients to make pancakes, how many pancakes did we actually make? We made 15 pancakes. We only had enough flour to make 15 pancakes. So 15 pancakes is what we're going to call the theoretical yield. And we're going to call the 3 cups of flour, we're going to call that the limiting reagent or reactant, because it's the one that determines how much we can actually make, determines what the theoretical yield is going to be. 10 eggs said we could make 25 pancakes, but we could only really make 15. Now we could go through, and if this was Chem 1, this would definitely be part of something that you would have to learn how to do, is we could go through and figure out how much of the leftover reactants there are. And that would involve saying, okay, well then how many eggs does it actually take to make 15 pancakes, and then how many eggs are left over? How many teaspoons does it actually take to make 15 pancakes, and how many teaspoons are left over? And we would use stoichiometry for that, 100%. Okay, so the limiting reactant is what runs out first. The number of product that limiting reactant makes is what we call our theoretical yield. Now let's take another example. Let's say that we cook our pancakes and we accidentally burn 3 of them and 1 falls on the floor. So even though we have enough flour for 15 pancakes, okay, let's say that we finish with only 11 pancakes. We would call that the actual yield. And again, it's silly to say that I burn some or drop some. I always, whenever I teach this in person, I usually do pizzas instead of pancakes, and I just say my mom makes all the pizzas and then she drops them. But whatever. In a chemical reaction, this is more likely. Not all reactions go to completion. Sometimes they're temperature dependent, sometimes they're concentration dependent. And so often your theoretical yield is the maximum amount that you'll get, but you rarely ever get that maximum amount. And so whatever you do end up with is called the actual. Now, for a cooking example, it makes sense. Yeah, we burn 1, or I make 12 cookies with all my ingredients, but then my kids come and eat 2 of them. So I only have 10 cookies, or something like that. And so in that example, we would have to figure out what the percent yield was. How much did we actually get compared to what we were supposed to get? And just like any other percentage that you guys, I'm sure, are able to calculate, you take what you actually got, actual over theoretical yield times 100. In this case, we actually got 11 pancakes. We were supposed to get 15 pancakes. 11 over 15 times 100, I got a calculator. It's 73%. So we had a 73% yield in this case. We had a 73% yield. Because 4 of the pancakes got ruined. So the actual yield of a chemical reaction must be determined experimentally. And it depends on the conditions, like I mentioned. It's usually always less than 100. Some product doesn't form, and some product is actually lost in the process of recovering it. Let's say that I'm making some crystals, and I can make 100 grams of crystals. Well, some of them might stay dissolved in water. Some of them might stay on the sides of my container. Some of them will get lost in all my transferring, and I might end up with 85 grams of crystals and not 100. So that's just the nature of chemical reactions. So to summarize, the limiting reactant is the reactant that gets consumed completely, or the one that runs out first. The theoretical yield is how much product we can get from that theoretical, or from that limiting reactant. The actual yield is going to be the amount we actually get. The percent yield is going to be the actual over the theoretical. All right, let's try some problems. Let's do a limiting reactant problem and a percent yield problem. That's a mole-to-mole problem. So this one doesn't involve grams. So actually, so we're going to do some problems. So the first problem here we're going to do is titanium solid and 2 chlorine gas molecules to form titanium chloride solid. So we've got 1.8 moles of titanium and 3.2 moles of chlorine. So let's find the limiting reactant and the theoretical yield. Okay, so I'm going to start off with the titanium. I know that I have 1.8 moles. My balanced formula, it is balanced. And you should always check it to make sure it's balanced. But 4 chlorines on both sides, 1 titanium on both sides, it's balanced. This says 1 titanium makes 1 titanium chloride. So if I've got 1.8 moles of titanium, and it says 1 mole titanium makes 1 mole titanium chloride, then I still have 1 mole of product, or 1.8 moles of product. So 1 to 1. So moles of titanium goes away, 1.8 moles is now of titanium chloride. So that's how much I could make just based on the titanium. We don't have our answer yet. Let's look at the chlorine. So for the chlorine, I've got 3.2 moles of Cl2. Now, this balance formula says that every 2 moles of chlorine gas only gives me 1 mole of titanium chloride. So TiCl4 on top, 2 moles of Cl2 on bottom. 3.2 divided by 2 is only 1.6 moles of titanium chloride. So in this example, we see that the limiting reactant is the one that runs out first and makes the least amount of product. So in this case, the 1.6 moles that we end up with is the theoretical yield. And because it came from the 3.2 moles of chlorine, that is our limiting reactant. It's limiting because it ran out first, and the least amount of product is our theoretical yield. Now, in many industrial applications, the more costly reactant, or the reactant that's most difficult to remove from the product, is chosen to be the limiting. When working in the laboratory, we measure the amounts of reactants in grams. So to find the limiting reactant and theoretical yield from initial masses, we have to add 2 steps to our calculations. So let's do it. So let's do a problem with this balanced equation. Sodium plus chlorine, actually, is it balanced? It is not balanced. Notice that this requires us to actually balance and put a 2 in front of the sodium. 2 sodiums and a chlorine gas makes 2 sodium chlorides. All right, we've got 53.2 grams of sodium. We have no idea how many moles that is. We're going to make a calculation. 22.99 grams of sodium is 1 mole of sodium. According to our equation, 2 moles of sodium makes 2 moles of NaCl. And then we're going to say that 1 mole of NaCl has the weight of 58.44 grams. That way we can get an answer in grams here. Now we could find out the answer to both of these two limiting reactant and theoretical yield questions without doing that last step. Once we know the moles, we know which is limiting and which is the theoretical yield. But in a gram problem, especially if this was on an exam or a quiz, the answers might be in grams, and so you'd want to take it all the way anyways. Okay, let's do the next one. We can solve them at the end, or you can solve them, and I'll write these out. So we've got 65.8 grams of chlorine gas. Now here's something I want to point out before we get an answer. Often you'll look at your initial amounts and say, oh yeah, one's more or less than the other. Don't let that influence your decision on which one's limiting. Right now it looks like sodium's limiting because we have less amount of sodium. But that may not be the case. Let's see. So this is a 70.90 grams for every mole of Cl2. Remember the molecule Cl2, not just the chlorine atom Cl2. 1 mole Cl2 will give us 2 moles of NaCl. That makes sense. There's 2 chlorines in a Cl2, but only 1 chlorine in a salt molecule. And then same thing here, 1 mole of NaCl has the weight of 58.44. Okay, so if you do the math, we end up with 135 grams of NaCl from the 53 grams of sodium and 108 grams of NaCl from the 65 grams of chlorine. So limiting reactant was actually the larger weight chlorine gas, and the theoretical yield is the 108 grams of NaCl. So again, we have to take them all the way to the end of this stoichiometry to see which one will run out or make the least amount of product. Now, as far as a theoretical yield type problem goes, let's expand this. So let's say that in this problem, the actual yield, okay, let's say that the actual amount that we got was 86.4 grams of NaCl. What's the percent yield? What's the percent yield? So we would take the actual over the theoretical. We would take 86.4 over the 108 times 100. .0%. I left off a sig fig. So if you are going to answer a theoretical or a percent yield question, then you're going to have to be given an actual amount, because that part you won't know. Likewise, you might be given an actual amount and then given some starting amounts, and it would be a combined problem where your ultimate goal is to get the percentage, but the number you don't know is the theoretical yield. You have the actual, you don't know the percent, but you know the theoretical yield. And so then you would have to do the work, that we just did to get that theoretical yield. One last type of problem is where they give you the percentage, they tell you the actual amount that you got, and then ask you how much sodium did you start with. And that kind of problem, if you can see here from this equation, if you have two things like the percentage and the actual, you just rearrange to get the theoretical. And once you've gotten your theoretical, it's like starting here and working backwards to figure out how much reactant you had. And if you wanted to find out how much reactant you had, then you would just reverse these calculations. So those are the types of problems that you would, tend to see doing these types of things. Now let's do another one. Now this one we're going to tie it all together. So this one we're going to we're given gram amounts of both of these reactants. We want to find the limiting reactant and the theoretical yield. All right. So let's see, and then we'll do an actual yield problem on this one too. Okay. So let's start. So we've got 8. So first we should see if it's balanced. 1 copper, 1 copper, or 1 carbon, 1 carbon, 2 coppers, 2 coppers, an oxygen, an oxygen. Okay. We've got 8.6. Oh no, that's not right at all. We don't have 8.6 anything. Sorry. We've got 11.5 grams of copper 1 oxide. And we've got 114.5 grams carbon. So I'm going to go through here and fill in all the molar masses. Sorry, that was wrong. I put that in the wrong spot. Let me fix that. I was doing carbon in my mind. All right, so this one is 1 mole of copper 1 oxide, and that actually has the mass of 143.10 grams. That gets us into moles of our reactants. Now we need to react or relate them to the product. In this case, they want to know how much copper do we end up with, or which one of these is the limiting and how much copper will be our theoretical yield. We don't have to pick copper, to be honest. We can pick any one of these products because the less amount of product formed in either case will still reveal to us which is the limiting reactant. We're just going to pick copper here arbitrarily because it's one of the products. So I'm going to relate my moles. So 1 mole copper 2 oxide, copper 1 oxide gives us 2 moles of copper. All right, and in this case, let's go one more step and say 1 mole of copper is actually going to have the mass of 63.55 grams of copper, Cu. All right, and then for the carbon, we see here that every 1 carbon produces 2 coppers. And then the same conversion at the end. 1 mole of copper has the mass of 6355. All right. So the main conversion factors here are, again, obtained from the balanced equation. And then we needed some molar masses. We needed to get the molar mass of copper 1 oxide, the mass of carbon, and the mass of copper. If we were using carbon monoxide as our product, we would have to get the mass of the carbon monoxide. Going through the motions here, we get 122 grams of copper from the carbon and 107 grams from the 101.7 grams of copper from the copper 1 oxide. So it turns out that the 101.7 grams is the least amount of product, so it's the theoretical yield. That makes the copper 1 oxide the limiting reactant. Now, if we actually got 87.4 grams of copper, then what would the percent yield be? It would be 87.4 grams over the 101.7 grams times 100. 85.9%. Percent yield is just like a regular percent. Don't confuse that with percent error, which you guys are doing in lab, which is different. Okay, so that is another example of how we do these conversions. Okay, let's talk about how heat plays into this. So we have a measurement called enthalpy. Now, enthalpy is the measure of heat that's evolved or absorbed in a reaction, meaning it's given off or it's released. Now, chemical reactions can be exothermic. That means that they emit thermal energy. They can also be endothermic, meaning they absorb thermal energy. And the amount of thermal energy emitted or absorbed by the chemical reaction is quantified with a function called enthalpy. Now, we define the enthalpy of a reaction as the amount of thermal energy or heat that flows when a reaction occurs at a constant pressure. Now, that's important because when there are changes in pressure, there are other factors at play. And so we don't talk about enthalpy unless there's a constant pressure. Now, the signs of our enthalpy can be positive or negative, and that depends on the direction in which thermal energy is flowing. Energy flowing out of a chemical system is like a withdrawal and carries the negative sign. Okay, so when enthalpy is negative, it is when it's leaving a system. Energy flowing into the system is like a deposit, and it carries a positive sign. Exo, of course, means out, endo means in, and in an exothermic reaction, energy is released to the surroundings. In an endothermic, it is absorbed from the surroundings. Okay? So I've got two examples of this type of thing here. So for the thermal energy flowing out of a reaction and into the surroundings as an exothermic reaction, the delta H reaction is negative. And the enthalpy of the reaction for the combustion of methane, for example, to give you a real number, which is the main component of natural gas, methane, is delta H reaction negative 802.3 kilojoules. What that says is that 802.3 kilojoules of heat are emitted when 1 mole of methane reacts with 2 moles of oxygen. So according to the balanced equation, we can even say this is the amount of heat released when 1 mole of CO2 forms. This is the amount of heat released when 2 moles of water form. It's related to those stoichiometric coefficients, just like we were doing with reactants and products. On the endothermic side, when thermal energy flows into a reaction and from the surroundings usually get colder, and we have a positive sign. Now here's an example. Nitrogen gas and oxygen gas combine to form nitrogen monoxide. This pulls energy in from the surroundings. It actually pulls in 182.6 kilojoules for every mole of N2 that reacts, or every mole that O2 that reacts, and for every 2 moles of NO that form. So the amount of heat emitted or absorbed when a chemical reaction occurs depends on the amount of the reactions that are actually reacting. So when I say that it takes 1 mole of N2 to absorb this much heat, well, what do you think 2 moles would do? Or 10 moles? Or half a mole? This number would adjust accordingly. If there was 2 moles, this would be times 2. If it was 10, it'd be times 10. If it was 1/2, it would be divided by 2. So that number is, what's the word? Proportional. Okay, so the magnitude of delta HRX is the magnitude is for the stoichiometric amounts of the reactants and products, the way that they're written in that equation that you guys can see. So let's try doing an example. So first off, we've got, we should probably go back to an equation. Let's talk about a balanced equation for the combustion of propane. So propane exists as C3H8, and this reacts with O2 to form CO2 and H2O. Now we should balance that, and when we balance it, we get that there's 5 O2s that have to react, 3 CO2s, and that makes sense because there's 3 carbons in our propane, 4 waters, that's 8 hydrogens, and there's also 8 hydrogens in our propane, so that helps, and then making the O2 match all the O's. This releases, okay, this has a delta H reaction, negative 2044 kilojoules for every mole of propane, for every 5 moles of oxygen, for every 3 moles of CO2, etc. And we can make conversion factors between any one of these things and our heat, the way that we are doing it here. Here. So for example, if the question said, how much heat is released for the complete combustion of this much propane, we would first have to figure out how many moles of propane we have. So the first step is taking the grams. In this case, it's 11.8, 11,800 grams. 11,800 grams of propane divided by its molar mass to figure out how many moles that is. Let's see, what is that number? Do we have that number? We can do that. 11,800 divided by 44.11, which is the molar mass. That's 267.5 moles of propane. Now the last step is saying every mole of propane combusted would release 2,400 kilojoules. So we just do another step, times 2044. So this would release negative a bunch. It's 5, let me see, 1, 2, 3, 4, 5. 5.47 times 10 to the 5 kilojoules, or 546,797 kilojoules. So a lot of energy is released by a lot more propane. Okay. Yeah. So if we do that, you can see the math. The negative number here is to tell us that this was released. It would not change the number at all if you left the negative off. We would still know that this was released because we're talking about a combustion reaction. But if you were simply going to show this, the negative does tell somebody that that was heat released and not heat absorbed. So it's important to show those negative symbols. Okay. Now, a little bit more before I end here. So let's talk about some symbology. Often Q or Q is used to show, the absolute value of Q. This is what those lines mean. Absolute value just means don't show a negative. This is often used as the symbol or sign for heat absorbed or given off. And we'll look at an equation, Q equals mc delta T in lab. I think we've already looked at this in the heat and energy chapter, but this is why Q has always been energy, or at least heat energy. We saw it as a lowercase q, here it's a big Q. Okay, so in review, we went over stoichiometry. Balanced chemical equations give quantitative relationships between reactants and products. We looked at limiting reactant, which is basically the smallest amount of product that gets made. Theoretical yield is the amount of product that can be made based on the limiting reactant. limiting reactant is what runs out first. Theoretical yield is the smallest amount of product made. Actual yield is just how much we actually produce or obtain, and percent yield is the actual over the theoretical times 100. We looked at reaction enthalpy, heat released, exothermic, heat absorbed, endothermic, and how to relate those enthalpy values to a typical problem. Just to give you another idea of that while we're talking about it, let's see. I could also ask you, I could say, there was 5,000 or 5,900 kilojoules released. How much propane must have been burned? And we would just start here. We'd flip all of these upside down and go backwards. And we would divide this number, right, by the negative 2044. And that would tell us how many moles of propane there was. And then we would divide that number by the, or we'd multiply that number by the 44, and that would tell us how many grams there was. So we would just work backwards. We could also ask about how much oxygen there was. And you would just, once you found out, you would have to look at the relationship, right? It would be 5 moles of oxygen instead of the 1 mole of propane. So from this number, we could still figure out how much oxygen moles there was, and then how much grams of oxygen there was. Those are the ways that you would move forward and backwards on these problems. And no matter what problem we do, you should always try to work them backwards, because your book is going to give them to you forward and backwards, because you need to know them forward and backwards. That's going to help. There is no real forward and backwards. We could turn a reaction around and just look at it the other way, and suddenly your products are your reactants, and your reactants are your products. So that's the point. You need to be able to move in any direction for whatever suits your needs. So hopefully these learning objectives will be useful to you guys. And again, that's it. So I will see you guys in the next video. Make sure to post any questions you guys have, and keep doing those practice problems, because those are going to help out a lot. And like I said, this is not Chem 1, so I'm not going to ask you to do some of the more difficult of these type problems, but anything that you find in your book is definitely fair game. All right, guys. See you next time.